something which I visit an email, we can follow in things. Just I thought it's good enough. So no technical things. Calculations must be wrong. But let's go to it. That message. And hopefully will be appreciated to appreciate it. So it's fine, sir. Hopefully, let's try to make this how more. And this is again not related with the technology. Again, it's related with the overall very much macroeconomic level. That's how the world is moving from prehistoric age to this. And this is very much a directional slide. So nothing technology in this, but it gives us a sense that in which the world is moving. It might be a very irrelevant or it's a coincidence, but I see a very good coincidence. We started with a wood when our only source of fuel was wood, which is having a carbon, and typically we see that ratio is 10:1. And with the difficulty of 300 years length of process, we slowly moved to 10:1, to gas, 4:1. Now we are moving towards, basically, if this trend continues, and which is more or less in a straight line, that when the economy and the fuel and the civilization is moving from 1800 till date, definitely we will hit hydrogen economy. Now this is an assumption, this is a pre-assumption, not even assumption. This is a forecasting, or you can say anything. But hopefully, if the mathematics tells the truth, I should move towards the hydrogen economy. And that should be very fast. This is a food for thought. There will be a lot of deliberations on these. Let us not get into argument over this slide, but we can really think over it. Now let me see something opens up over here, and if it opens up, let's see.
Even with the strongest imaginable efforts to convert to alternative sources of energy, fossil fuels will continue to be the primary source of energy for decades to come. Addressing the greenhouse gas emissions of fossil fuels, however, is a significant challenge, requiring a range of responses, including greater energy efficiency and new clean energy technologies. Carbon capture and storage, or CCS, captures the most common man-made greenhouse gas, carbon dioxide, before it can be emitted to the atmosphere, and injects it deep underground to be stored in geological formations. It is the only technology available that can make deep cuts in greenhouse gas emissions from fossil fuel-based energy production, and will be an essential part of the global clean energy portfolio. Among dairy farms in southwest Victoria, the CO2 CRC Otway project is Australia's first demonstration of the deep geological storage of carbon dioxide, or CO2. The project provides technical information on storing CO2, as well as monitoring and verification programs and processes. This is helping inform public policy and industry decision makers, while also providing assurance to the community. The project provides an ideal base for ongoing research into the geological storage of CO2. CO2 CRC, the Cooperative Research Centre for Greenhouse Gas Technologies, leads the Otway project.
CO2 CRC is one of the world's leading research organisations in carbon capture and storage. The Otway project is an international collaboration with scientists from Australia, New Zealand, the USA and Korea. We bring together funding from members, we've got over 30 members, as well as from the Victorian and Australian governments.
During stage 1 of the project, over 65,000 tonnes of CO2-rich gas was injected into a depleted gas reservoir 2,100 metres underground, where it has been safely stored and monitored. As injected CO2 is buoyant, it rose to the top of the formation before being trapped by a thick layer of impervious rock.
We started planning for the Otway project in 2003, and it's apparent right from the start that we have to work very, very closely with the community. It's their community, it's where they work, it's where they live. So we had to provide them with the assurance that it was safe and secure to inject carbon dioxide into the ground. We did this through monitoring. We have a very rigorous monitoring program in place. We monitor the deep subsurface down to 2 kilometre depth, and we monitor the deep groundwaters, we monitor the shallow groundwaters, we monitor the soils, and we monitor the air. So we're very, very confident that we're not getting any leakage of CO2 into any of these environments.
The project has produced a range of significant research papers and reports, and has been an important factor in developing Australia's world-leading CCS regulations and legislation.
Stage 1 focused on CO2 storage in the depleted gas field. Stage 2 focused on CO2 storage in deep hotspot formations filled with water. And these formations are very common worldwide, and they form 90% of the global CO2 storage capacity.
Commercial CCS projects need to know they've got a site that's secure and won't leak CO2. They need to know they've got adequate injectivity, so they don't need too many expensive wells, and they need to know the capture is sufficiently close so they don't need excessively long pipeline. Stage 2 is about demonstrating residual trapping.
As a long trapping occurs when a small amount of CO2 becomes disconnected or snaps off from the stored CO2 as it moves through the porous rock. Tiny bubbles of CO2 are stored in the pores, trapped by surface tension. The CO2 can't move out of the pore space and remains fixed underground. To find out how much gets trapped in this way, an international team of scientists planned a series of experiments at the Otway project. A new injected well was drilled to over 1,500 metres, following comprehensive surveys of the reservoir intended for storage.
During the drilling process, a sophisticated set of wireline logging equipment were loaded into the well to get a detailed set of records of the water. In addition, 176 meters of core were extracted.
The core and logs provided real-world data that were used to fine-tune computer models of CO2 storage, how much the formation could hold, how the CO2 would behave underground, and how it was trapped. The next step was to install a sophisticated 28-metre downhole instrument assembly, 1,400 metres underground in the new well. The instruments included pressure and temperature gauges, as well as a world-leading sampling system known as a U-tube system. Once the downhole instruments had been installed, the stage 2 experiments began. To measure the stored CO2, a series of extractions and injections were undertaken over a 2-month period. First, formation water was extracted and stored on the surface in tanks for injection later in the experiment. In addition, the downhole instruments gathered information on the rocks in the water-saturated formation. Noble gas tracers were added to learn more about the reservoir and the residual CO2. A relatively small amount of pure CO2 was then injected into the formation to mimic a commercial CCS operation. After a period, formation water saturated with dissolved CO2 was re-injected into the well. The injected formation water breaks up the mobile CO2 plume, leaving residually trapped CO2 permanently stored in the pores of the rock. Several approaches were used to evaluate how much CO2 had been permanently trapped. Measuring the CO2 content of water extracted from the well showed how much CO2 was left behind. Pressure was continually measured by very accurate downhole and surface gauges throughout the experiment. The detailed temperature profile was measured. Samples of water and gas were taken from the well using the U-tube sampling system and then analysed for tracer gases and CO2. By using all these methods, researchers could compare different approaches to determining the size of residual trapping.
The Otway project has allowed us, for the first time in the world, develop a suite of technologies where we use a single hole to assess the potential of a significant area of rock.
Pathway Project researchers have been able to correlate the results of these experiments with their understanding of the formation rock qualities to estimate the storage capacity of the formation and extend that knowledge through modelling to other similar formations. They also learned a great deal about how carbon dioxide is trapped in solution in the formation. The work has allowed CO2 CRC to produce practical tools for commercial CCS projects that will make it easier to evaluate potential reservoirs. With a proven record of scientific excellence, the CO2 CRC Pathway Project is an ideal facility for continuing research into the geological storage of carbon dioxide. CO2 CRC and the Otway Project are demonstrating that carbon capture and storage is a safe, practical and effective clean energy technology.
Project of CO2 carbon capture and storage, and we can start with a bit of discussion now before we go on to the capture work. Because today, in the next 1.5 hours, we'll be discussing about how we capture CO2, and tomorrow we'll be discussing on how we store that CO2. And in the afternoon, after lunch, we'll be listening to the Global Director of CCS, Alstom, what about other projects, his projects of 6 CCS projects. And then we'll be listening to IEA, International Energy Agency's Team Dixon on CCS in Sydney. So definitely now in the next 1 hour, what we are going to do, we are going to talk about the carbon capture portion of this. Bit of storage nomenclatures, because when Team Dixon, I expect he is going to talk. He is going to talk a lot about the international negotiations, so we will try to get, before he speaks, we will try to get a briefing among ourselves, so we are in line of what he is trying to convey us. And before we proceed further on the subject, any of the views or questions on the CCS, how we are pursuing, etc., so we can go before, we can discuss that before we go ahead. So the floor is up to you, sir. Any of the things, please.
It's good.
Yes, please.
Underwater plants and the surface water plants. Even underwater plants do photosynthesis.
Yes.
On that thing they need the carbon.
Yes.
Can't it be matched? Can't it be balanced? So that carbon dioxide emitted into the water is used with the plants for the purpose of photosynthesis. Maybe used. But all carbon dioxide is stored beneath the ground. The tanks, water reservoirs, lakes can be used so that what carbon dioxide that escape will be used by the underwater plants. The remaining carbon dioxide can be protected from coming out of the lake by surface water plants. Is that feasible? Is there any study of that?
I think, sir, I will not. If it is your idea, and I know you are not a technical person, sir, but if it is your idea, then I need to select it. Only because there is a huge plan of CO2 capture to algae. But you are telling absolutely that is under not only plan, people are implementing it. So I think your thought is absolutely on the right direction. And yes. Now what is happening? There is a huge amount of algae production is there. So you are capturing CO2, putting into water, putting in algae which are very fast growing algae. They capture that CO2, convert into chemical energy. And this pilot project already taken up by NTPC, first one, in India. Second pilot plant has been initiated, not only initiated, implemented by Bombay Tata Power. Dr. Avinash Patkar is looking after that project. Globally, there is a lot of other CCS plants. They are talking about algae in the open, not only in the reservoir, they are talking about in the open sea algae productions, because it is having a huge potential to capture that CO2 and convert into chemical energy end of the day. And these algae, say Tata Power algae, they are taking it up again because regular interval, and they are converting into biodiesel, and after the biodiesel they are converting into a food grade. So it's a frozen food and it's a very highly rich. So I think if you are thinking about this, you are very in the right direction.
Even those plants can be commercially exploited.
Yes, that's what they are trying to do. Algae, what they are choosing algae? Algae is the fastest growing among the green habitats. They grow very fast. Within one night they can grow amount of growth, though they are small, but from the micro to sizable, considerable size, they grow very fast. Right. Anything else, sir, before you pass it on? Okay. Then let us talk about that again today in the core of the subject, that what is the typical CCS project, carbon capture and storage, and how do we? Now there are two aspects of this. One aspect is that first one, let us talk about what is the sources of CO2. The sources of CO2 we know definitely. One is anthropogenic CO2 and which is non-anthropogenic CO2. It's what is man-made and what is not man-made. The anthropogenic CO2 is coming basically from our fossil fuel combustion and the processes. So, which is the fossil fuel combustion in the power sector or in the non-fossil fuel, non-power sector, which is typically cement. Cement, the process is there. We are getting calcium carbonate, CaCO3, and which is beta-benzyl CO3. When we heat data, we get CO plus NGO, and CO2 goes out in the atmosphere. So, cement kiln is one of the process where we get almost a pure CO2 coming in, though you have combustion CO2, so the purity drops down, but it's a considerable pure CO2 coming out from the cement plant. The other thing is the steel plant, where we have to do reduction. If to Fe2O3 or Fe3O4, we reduce to Fe, and where the reduction agent is primarily carbon. We are talking about the hydrogen-based reductions, which is ALGOS project, which is going in Europe. But before that, it's primarily basically carbon monoxide-based reduction. Now, the CO-based reductions ultimately convert to CO2, and if it is gas-based DRI plant converted to again the CO2, we are getting almost 98% pure CO2 coming out from the steel plant. That's a huge amount, because we are talking about something 2 tons of CO2 per DCS, ton of good steel, which is in very good steel plant in India. If we talk about the cell, it is coming to 2.8 tons CO2 per ton of good steel. But on the other hand, it is normal oldest steel plants like steel, they are coming around 2 tons of CO2 per ton of good steel. And SI in the gas-based DRI, they are coming around 1.3, 1.4 tons CO2 per ton of good steel. However, this CO2 is almost pure. Now we are talking about, we are having 54 million ton of, now it is I think 65, but 54 million tons of crude steel produced every year, which means we are getting 104 million tons of CO2, which is almost pure coming into atmosphere. So that's the amount of single concentrated source of CO2 coming in the atmosphere. And third is aluminium. I think we are having almost 4 million tons per annum of aluminium production. Again, if you know, many of you are conversant with aluminium process. We are getting aluminium as a raw material, aluminium is mostly, and then we are basically electrolyzed. And during the electrolysis, we are getting two things. What is the perfluorocarbon we are getting out, and second, we are getting out another pure stream of, this is almost again 94 to 95% pure CO2 we get from the flue gas, exhaust gas of ammonium. Now, and the other portions, obviously we talked about the biomass, which is the biomethanation, especially from the breweries. So wherever we are producing whiskeys, malt, beers, in the biomethanation process, we are getting a huge amount of CO2 coming out. Again, this CO2 is very pure, and however, there is a huge utilization of the CO2, which is in the food grade CO2. They are typically, and they are used for soft drinks or aerated drinks mainly. And there is another use of these, they take it from for the extinguishers. So these two are the more or less the CO2 for anthropogenic sources. Now once we get the sources, and obviously our power plant. Now one of the things let us discuss on the power plants. The power plant CO2 is a very bad CO2. For whenever we are talking about the carbon capture and storage, power plant CO2 is just for coal-fired power plant. We are getting around 20% of oxygen. Then we have to fire excess oxygen to complete the combustion. So concentration of CO2 what we get is maximum up to 15%. We don't get more than 15% of CO2 concentration generally in the power plant. If it is gas-based power plant, then the situation is even worse. Because the gas carbon goes down, it's even lead CH4. So instead of Ce, it is going to CH4, we get a hydrogen component in E. So we are getting roughly 5 to 6% of CO2 concentration. Now think about this. Once we talking about the carbon capture and storage, typically we want to concentrate only on CO2. Definitely nitrogen is not of use. So the main purpose is just like coal washer we discussed in the morning. Main purpose is to segregate that one CO2 with the nitrogen. Let's see how do we do this. Did we do this? The point is, I think the last time also it is the reputation. We have around how much now? 7 billion or 8 billion people in the world, 800 crores. Out of that, if we say in this room, everybody of us, we are washing our clothes at least after two uses or 3 uses. We use soda ash, or soda, or salt, Excel, NaL, whatsoever. Now, how do we get this soda? Which is nothing but sodium carbonate. How do we get it? Typical reaction is, first we get calcium carbonate, which is limestone in the process. It's called solvent process basically. In the CaCO3, we heat it up. We get the limestone, we heat it up, we get CO plus CO2. This CO2 which is going out, it is being captured. It is being, because it's the number one, it's a pure CO2. You are getting limestone and you are heating it up. No oxygen in that container, so you are getting pure CO2 coming out of the gas and you capture it out. You cool it, you capture it. This is step 1. What do we do with the CaO? We mix it with water and we get CaOH twice. We put it in a tank. With this CO2, we get ammonia. We get ammonia plus water plus CO2. Once we get the ammonia stream, CO2 stream mixed with the water, we get first ammonium carbonate, NH42 CO3. This ammonium carbonate further reacts with CO2 and H2O, we get ammonium bicarbonate, NH4HCO3. This ammonium bicarbonate, when reacts with the sodium chloride, which is plenty available in the seawater, basically what we need to do the grind, that's why these typical soda ash plants or salt plants are in the coastal region. They get seawater grind solution, they concentrate it, evaporate it with the steam, get the concentration of sodium chloride. This reacts with that NH4HCO3, where we get sodium bicarbonate or sodium ciscarbonate and ammonium. Now this ammonium further reacts with CaOH twice. We are getting ammonia coming back, ammonia split. We get sodium ciscarbonate, NH4HCO3. Sorry, Na. Sodium, not NH4, ammonia goes out. And then sodium ciscarbonate, we heat it up, we get sodium carbonate, which is soda ash. So if this is the soluble process, and this is in operation for the last, how much years? 60 years or 80 years? 1920, I think the soluble process has been first. I think you can answer this better than me. So this is getting utilized in globally. So CO2 capture, typically what we are doing, it is in operation for a very long time. It's a very long time CO2 capture is there, and as on date, whatever the CO2 capture is in place, it is more or less the same technology, which is commercially available. We'll discuss that. We'll be talking about that. But this is the more or less the equations we are doing, and we are doing it past at least 60 years coming up with this. Now, what is the other type of? No. We talk about the three combustion. One in the CCS, one on this slide. We talk about the two things always, because these are the really people like to talk about the high level. So we talk pre-combustion and post-combustion CO2 capture. Basically, our aim, the base aim is that getting a pure CO2. Now there are two options. Number one, once we get the flue gas from the thermal power plant or the process heat, this gas is mixed with other gases, we need to separate CO2. Now after the combustion of everything, and when we try to get a CO2 from the flue gas, we are terming it as a post-combustion things. What about the pre-combustion capture? It is nothing. Pre-combustion is that we try to separate carbon from the other things, other elements, and then we try to go for CO2, which is termed as a pre-combustion. So how it can be possible? Yes, see, we are talking about the same fuel, same methane. Now, if we are really talking about the natural gas, we can really segregate hydrogen and carbon separately. Then we can use that carbon for CO2, and we taking out the hydrogen separately. We can be more or less ensured that how much CO2 or we can have, which is termed as a pre-combustion CO2 capture. What is the example? Example is we are already designing, which is under commissioning, which is a hydrogen-fired power plant. Now, this technology is old and new. Again, this reforming and this is very common in the urea plant. If we are talking about that all the fertilizer, urea fertilizers we are using, we are actually doing cracking basically the natural gas, and the name is cracker basically. We are taking carbon separate, we are taking hydrogen separate. In the urea plant, actually production, we are again getting CO2. We are mixing with ammonia, and we are manufacturing our ammonium nitrate. That is carbonate. Here we are talking about nitrate, which is used for the nitrogen fixing, and we use as a fertilizer. And typically in this country, when you talk about the MHI, Mitsubishi Heavy Engineering, and they actually one of the now CO2 capture CCS project. They are one of the largest contender of the technology suppliers. Two of their largest installation on globe. It's very basically in India. One is in Nagarjuna fertilizers, and one, I think two is in Nagarjuna 3 in IFCO, Aula and Kulpur. They have already installed 450 tons per day CCS plant, carbon capture plant, but storage is through urea manufacture. So again, the topic is a pre-combustion capture, but the technology is basically you are cracking out carbon from the rest of the element, and then you are producing CO2, and this CO2 you capture. And the process requirements of urea, they need to basically almost pure CO2, 99% pure CO2 to be react with nitrogen, and you get nitrogen of the air and they are at temperature, and they invert it ammonium nitrate. Now, third one, we are talking about the oxy-fuel combustions. We think about we are talking about the one. This oxy-fuel combustion is again nothing but enriching the CO2 percentage in the flue gas. How can we increase the 15% of CO2 in the flue gas from a power plant? We go to 20%, 25%, 30%. The only way is that if we can enhance oxygen percentage in this, or basically that means we are reducing the nitrogen component out of this. So if you can reduce nitrogen component in the gas, and once we react with the coal, obviously the amount of CO2 percentage goes up. Now when we will be talking about that CO2 absorption through amine, we can find it out that the cost of capture is basically proportional to or inversely proportional to percentage of CO2. So the more is the percentage of CO2 in the flue gas, cost of capture comes down. And if you are talking about the entire CCS project, carbon capture is the costliest part out of this. Because waste part is easy. Waste is once you get the CO2, you have to pressurize this, 180 bar, 200 bar, you have to put it dense cells. Let us in fact we'll talk about that separately. And then you put down in the reservoir, which we talked about, 1 kilometer, 2 kilometer down the reservoir, and you let it rest. So the waste part is not that tough in that project. Because oil holes or drills, these holes, they already exist. We are not going to do a separate drilling specifically for CO2 injection. What we will do, the depleting gas or gas reservoirs, already you have multiple wells over there, holes. They are using those wells, putting the CO2 in. So the cost of drilling is not that much. Cost of putting in is the pumping. But in the whole value chain, cost of capture is the most significant one. So that's why I think one of the questions comes that why not steel and cement plant? And in Abu Dhabi, what we did back, in Abu Dhabi we targeted Inuit Steel company, which is a 6 million ton steel plant, where we are getting 0.8 million ton pure CO2. We are just taking it up, scrubbing it, cooling it, transporting the site and putting it down. That's the best part of the demonstration we could do it. And the good part of this, we use this as an enhanced oil recovery. So, which each ton of CO2 putting in, we are getting some amount of oil coming out. So that gives the extra money, and that actually supports the project. Abu Dhabi National Oil Company had given us that time $30 per ton of CO2. That the price they have given. So, if we are talking about that, what is the cost, this one of the government cost, and that is not a profitable project, but that we can talk about that what is the oil coming out, this is what is the cost balance. A very simple answer is $30 per ton of CO2 made us cost benefit. Obviously, in India it will be cheaper because we had fat salaries in Abu Dhabi, India, those are things. So that component will be equivalently cheaper. Because in one power plant over there, it talks about around 3 million per megawatt, which is much less in India, on the same process and everything. So that's an economic difference. So you can apply to it, but it's a $30 per ton. In Abu Dhabi, we got it. Now, with that background, let's come. Now, any of the questions till now, so that we can proceed before we proceed further.
May I ask this?
Please, sir. Otherwise, I am thinking that I really speaking, I am not sure whether I am telling wrong things or like this. I need reactions.
So, this radio frequency is used in this process here. Because radio frequency is widely used in most.
I think we have design. Why I'm telling, in the steel plant, when we use that, because I know one of the live examples where I was there. Because in the power plant this is a bit different because there is a load fluctuation and the amount of fuel will come in if it is not a base load station. But in that particular steel plant, we get a production schedule and we get more or less constant fluid output over there. So we couldn't use the variable frequency drive because it didn't make us economic sense. So we use compressor setting and even on the when we pump it down, again it's whenever we operate it, either we operate it or we don't operate it. It's not a continuous process, but it's a batch process. We get the CO2 and when we pump, it's like a constant pressure and constant delivery. Because when it goes down, it takes time to disperse. We have so mentioned this. It depends on the permeability of the rock because below ground rock is porous. And once you pressurize this, there is a particular speed at which the CO2 spreads. So it is all dependent on that speed and pressure, reservoir pressure. So we didn't use that very variable frequency drive. But I am not sure in the power plant because power plant, if it is a load fluctuating things, I might overdo my this. But one of the technologies where we are using pressure swing absorption for CO2 separation, I think that's an essential mode where you have to use variable frequency drive. Because the pressure swing absorption, alternately, there is a continuous change of force gravity. So there you can make a lot of benefit by using that. So anything else?
But where we are getting from the fuel? Either way, because after calcination process, most of the gases are going away. They are sending by kiln or somewhere some by it. Or sometimes they are sending by EST. So this is the way you are doing.
No. The thing is that weight process, as on that, I think India last one of the process was in Andhra and the plant has been closed. I don't think in India we are operating a simple weight-based process-based plant in India. As far as I remember, there is 2 plants are still operating in Egypt, which are weight process, which electricity and fuel. So they are getting obsolete nowadays. So as if we are talking from Indian perspective, we don't use any of the weight, we don't have any weight process. So let us exclude that completely. Typically because the cement plant, you are getting around 80 to 85 kWh per ton of cement, which is you are getting the electrical consumption. The best of the plant is obviously 65 kWh per ton of cement. And the thermal is around 650 kcal per kg of clinker. Whereas in the weight process, you can get up to 2000 kilocalorie per kg of clinker, which is much more, 3 times of thermal energy needed. And the electrical energy is around 160 to 180 kWh per ton of cement. So that's the reason weight processes are becoming obsolete and you don't find anything in India. I think still 2 are operating in Egypt, but they are also thinking of converting into the dry process. And so whenever we are coming to the dry process, it's the kiln, which is a kiln rotating. There we get the process CO2 coming in as well as the combustion CO2. The limestone CaCO3 first you get in the crusher in the raw mill. They are putting in the preheater line of the gas line. Then they come down and they are taken to the kiln where they are heated up to 1200 degrees Celsius and where CaCO3 is dissociated to CO plus CO2. This CO2 basically goes up along with the combustion flue gases and they are captured in the preheater exhaust. If you want to get it, you can capture it from this. But the concentration of CO2 is much more.
Thank you.
You're welcome.
Steel plants, last one is you do have the waste heat recovery system. So that mainly involves with carbon dioxide once again. So instead of using the waste heat recovery systems, if you use this CCS, how what will the difference that you find in a steam?
So your answer is over here. First one. The next slide. The thing is that we need a flue gas composition view of the characteristics. Number one, it should be in how do we use the flue gas? It should be used in a cold temperature. The typical absorption temperature. Because how do you separate CO2? Let us first talk about how do you separate CO2 from the flue gas. I am coming to your question. You can sit down. We get CO2 in the flue gas, and this needs to be absorbed with amine solution. Now, once we absorb the amine solution, the typical temperature range should be below 80 degrees Celsius. It's a condition is must to solvent absorb CO2. The condition is that you have to take below 80 degrees Celsius. Ideally, it should be 50 to 60 degrees Celsius. The cooler, cooler it is, it's better. If you want to maximize your productivity, you need to cool the gas. Now, how do you cool the gas? You take the heat out of it. Now, whether you waste it to quenching, or you take a waste heat recovery system and you take out the heat and you utilize this, and then on the cool gas you absorb it. So both systems can really marry each other. It's not that they are going to do opposites. Where the waste heat recovery is needed. In the ESI steel plant, the waste gas was coming out around 420 degrees Celsius. This 420 degrees Celsius was cooled through waste heat recovery system to 130 degrees Celsius, and this 130 degrees Celsius is used again for quenching, and then we get the scrubbing and we get the CO2. So waste heat recovery system is rather an integral part of the steel plant if we want to do a CCS with that.
So, like, what are the previous?
Yes, please.
These three, you were saying that higher the amount of carbon dioxide in the flue gas, it will be better. The CCS will come down, the cost of it. So, according to this, the third technology will be the best for it.
See, it depends. The thing is that again, you are talking about the power plants. If it is a power plant, yes, Asapur is the best because it is cheapest one. Let us talk about a few things. First one is the business as usual. So let us not discuss about this. What about the second portion is the quick combustion things. Now, separating CO2, C from coal, as we know that separating ash is such a difficult thing. So getting a pure CO2 is really, really tough from now. So it takes us, and if we are talking about the natural gas, is another feedstock. It's called cracking. And which is again talks about the energy loss and the money, etc. Third thing, ideally, this is an ideal one, because the moment you go for oxyfuel, the volume of flue gas comes down, and we know in the boiler the maximum loss happens in the flue gas, in the boiler circuit. So obviously you reduce the amount of flue gas, you improve the efficiency. However, what we have a limitation on the metallurgy as of yet. Because the moment we go for oxyfuel combustion, we are going for excess oxygen coming in, the temperature goes up. And if the temperature goes up, we are still having a problem of boiler cost. Because the metallurgical cost goes up. And second thing is that we have to understand there is the heat flux. Because with the high temperature, the heat flux goes more. And whenever you are putting water in your circuit, absorption circuit, water is having a particular rate of absorbing that heat. It cannot, if you are just like that, I can eat at a certain pace. If you give me too much food, that does mean I can enhance the bit more, but there is a limitation that I cannot take more than that. Similarly, if the water is here, water is having an absorption rate over there. So it actually limits the temperature. Otherwise, it will be what will happen, the more oxygen you flue gas temperature unnecessarily will go up. So if you can actually design your boiler where you have multi-bus water coming in, a huge amount of this, you design ideally you can go for 100% CO2, ideally. But it immensely increases the cost, material cost and the metallurgical cost because the temperature is up. So that limits, as on date, limits that amount of oxygen, but you are absolutely right, that should be the technology of the future. In fact, we are unfortunate not to get Linde. Linde is the world's largest oxy-fuel technology supplier, technology developers, and a chemical company, one of the largest in the world. This Mr. Joachim, who is basically heading the Linde oxy-fuel, unfortunately he could not come, but he promised that he will come to BHE. So if you can, and not necessarily he is here, and he can deliver his experience on the oxy-fuel, maybe in BHL or in Avicii individually, that can be arranged. So that you know exactly from the technology developers what is the limitation. They have already installed 2 of the systems, one in Kallani Forge in Pune, that's a steel plant. They have installed the oxy-fuel combustor, where in steel you have to reheat the ingots. These reheating furnaces, they have done the oxy-fuel things, and they have actually had a huge amount of monetary savings as well as the productivity went up. So your answer and question.